Good evening. Thank you all for coming. Thank you, Holmes, for kindly arranging this glimpse of the aviation revolution. I'm going to address just aircraft, not the important evolution of airports, route architectures, business models, sustainable aviation fuel, which dominates short-term climate solutions. And I will also ignore contrails, which it turns out can be almost entirely avoided by measuring humidity at the cruise altitude and adjusting that altitude for a few percent of the flights. So here's tonight's story. 20-odd years ago, electric road vehicles, EVs, were widely thought impractical in payload range and cost because batteries were inherently too weak, heavy, and expensive. But then smartphones spawned advanced batteries. Their higher energy density made EVs feasible. Mass production then made the batteries tenfold cheaper, making EVs affordable. And also, importantly, lighter and sleeker cars could drive farther on less energy, so they needed fewer batteries and saved more weight and cost. The driving range passed 300, 500, 740 miles. More efficient EVs with better batteries won on life cycle cost, and many cost no more to buy. Now remember, these were thought impossible, but now over 74 million EVs were sold through last year. Nearly 100 million are forecast by the end of this year. They're a quarter of world auto sales, over half in China. That is, in China, the market share is over half. And some even more advanced EVs, as you'll see, need so little energy that they can run largely or wholly on their own solar cells without plugging in. Now this automotive history is repeating itself in aviation. The same forces that created EVs are now enabling game-changing electric planes, which I'll call EPs. The EV and EP industries co-evolve swiftly with shared technologies, innovators, and supply chains. But EPs evolve faster because electric aviation enjoys ample capital, Silicon Valley speed, not Detroit speed, vibrant competition, and higher ambitions, as it must because it's harder. So I'll explain why EV's emerging evolutionary pattern will at least closely rhyme with that of EVs just a quarter century later. That's contrary to the widely held view that aviation will use ever more oil while road, sea, and rail transport use less. So in the second of these Bloomberg graphs, oil-based aviation fuel in magenta just keeps growing rapidly, and by 2050, it's only 7% displaced by bio-based sustainable aviation fuel in gold. But that projection assumes that aviation fleet efficiency will rise only 8% by 2050, far slower than historically. So let's see how to falsify this assumption and make the aviation graph look like the other three. I'm originally a recovering physicist, but for the past quarter century, I've been a practitioner of designing super efficient vehicles, buildings, factories, and equipment. And each winter and spring quarter, through so far 15 iterations, Professor Joel Swisher and I teach an experiential course on how integrative design can make the energy efficiency resource several-fold bigger, but at much lower costs, and often with increasing returns. That's because, as this paper shows, we use not more or fancier widgets, but fewer and simpler widgets, more artfully chosen, combined, timed, and sequenced. In 70-odd years of flying many millions of airline miles, I've also observed that airframe makers, although very skilled, could get better at integrative design. What's their challenge? How far do airplanes need to fly? Well, long routes are scarce. Of the 2023 global emissions of aviation carbon, over half came from short trips on narrow-body or smaller planes. That's the dominant 4 aqua bars on the left. Just a 2,000 kilometer range could cover 2/3 of the routes. Indeed, over a sixth of the emissions come from routes of 1,000 kilometers or less. That's a very big entry market to grow volumes, improve technologies, and cut costs. Now, we've actually seen this before. When Tesla introduced the first lithium-ion battery car in 2009, about 80% of U.S. car routes were under 20 kilometers. 96% were under 100 kilometers. The two-seat Roadster adopted electric drive in a lightweight Lotus Elise fiberglass and aluminum sports car, and that combination had an impressive 393-kilometer range, which made range a non-issue according to Car and Driver magazine. But many customers still worried about range, and there were no fast charging networks to plug into. The 53 kilowatt-hour battery pack was also expensive. The powertrain was handmade. So in real terms, the sticker price was 4 times that of a modern 4-seat Model 3. While providing ample range in practice to early adopters, Tesla needed time to build production volume and cut costs and reduce the energy use per kilogram by 16% and raise the car's top range by 40% for the rare but important long-range trips, and also to store 42% more energy per battery pack kilogram. So the dominance of short trips bought that time they needed, and now electric planes can apply the same strategy by starting with abundant short-haul markets and building out from there. However, unlike autos which ride on tires, planes need lift to stay airborne. Most aviation experts assert that for electric flight to get off the ground, if it ever can, it will need battery packs to store 2 or 3 times more electricity per kilogram than the best battery packs in today's EVs, and yet stay safe, durable, and cheap. That's not easy. It is authoritatively forecasted anyhow, but it comes from asking and answering, I think, the wrong question. It simplistically compares fuel with battery energy density and propulsive efficiency in today's aircraft, rather than redesigning the whole aircraft for electric propulsion. So it's a classic case of optimizing isolated components and thereby pessimizing the whole system. But integrative whole system design of far more efficient airplanes can make the battery needs very much milder. This was explained 12 years ago in a remarkable technical paper by 2 distinguished NASA Langley aeronautical engineers. They say electric aviation propulsion has compelling differences that will fundamentally alter the way propulsion integration is approached. Integrative design lets electric propulsion not only compete but far exceed existing propulsion solutions in many ways at battery-specific energy densities of only 400 watt-hours per kilogram, yielding 4 to 8-fold improvements in energy costs, they said, with dramatically lower total operating costs while dramatically improving efficiency, community noise, propulsion system reliability and safety, and of course, with zero greenhouse gas emissions if you power the planes with carbon-free electricity, which last year was 43% of world electricity and rising fast. These authors also said that for several initial applications, battery energy density was already sufficient, this is 12 years ago, for competitive products in some entry markets, and for many additional markets, energy densities, will likely be adequate within the next 7 years for vibrant introduction. That meant 5 years ago. So we'll see how that's going. And they're right, because electric propulsion does not just produce thrust. It also creates new advantages, new degrees of freedom, transforming how the whole aircraft is designed. So you cannot compare propulsion systems in isolation. The economics are also far better. The business opportunity is here and now, and thinking that it's far away risks grave disruption. I'm not implying here that battery energy density is not important, but rather that it's already adequate, as we'll see, if offset by whole aircraft improvements. Batteries do cost and weigh more. They don't get lighter as they're drawn down. They need meticulous safety and certification. However, electric propulsion has many offsetting advantages. It has a many-fold lighter weight powertrain and higher efficiency than fuels do, over a huge range of scale that invites distributed architectures, many small motors, not a few giant gas turbines. Efficiency stays high over most of the power range. Torque rises, thrust is widely available without gears, energy for climbing can be largely recovered on descent. No combustion also means no intake air and no exhaust. Reliability and safety improve through greater redundancy, radical simplicity, and major power surge capability. Noise and engine dependence on density altitude nearly vanish. Higher altitude is feasible. Maintenance shrinks. Emissions disappear. Energy costs, that is, price times use, fall by an order of magnitude. Capital costs shrink even more at low production volumes and can make electric airplanes better, safer, and cheaper than fueled airplanes. That's a lot of advantages. So, bypassing technical details, I'm going to offer some simple examples and analogies illustrating this logic. And while I will address mainly energy efficiency, remember that economics merit equal emphasis. There's a wonderful Volt interview, 19 June 24, with Dave Roberts, in which the leader of one of the best electric airplane companies called Beta, Kyle Clark, said two novel things. First, that electricity is about as much cheaper than fuel as batteries are heavier than fuel. And once you buy a battery electric aircraft, you can probably upgrade its batteries each decade thereafter to double its range and therefore quadruple the cities it serves, because that goes as the square of radius. So the electric plane adds ever more value, unlike fueled planes, which steadily deteriorate and shed value throughout their lives. That's a lot to digest, but let me take it apart into pieces for you. And just to get the physics right, I'll give you one equation this evening. Airplanes' fuel efficiency is proportional to three things: engine efficiency, which is the reciprocal of fuel use per unit thrust; aerodynamic efficiency, measured by the ratio of lift to drag; and a logarithmic term on the right, based on the ratio of fuel weight to gross weight, which is structure plus payload. And that third term is needed because the plane gets lighter as it burns up the fossil fuel and turns it into about 6 or 8% of climate change. So, putting aside that fuel burn and other complexities, the three prime variables here are propulsive efficiency, aerodynamic efficiency, and mass efficiency, or you might summarize as thrust, sleekness, and lightness. However, these three all interact, sometimes favorably, often not. Their interactions are complex. They need a full systems analysis. So the many technology and design opportunities I'll mention do not simply combine in a real aircraft at the systems level, nor do they combine simply across a full mission profile that includes not just cruise, but also conditions like takeoff and landing and maneuver. So keeping that caution in mind, now back to the story. Planes travel about 10 times faster than cars. For both of them, the aerodynamic drag rises as the cube of speed. And also for both planes and cars, reducing weight is crucial. Of course, the numbers differ for planes and for cars, but ultralight weight plus low drag crucially enables non-fossil fueled propulsion of both kinds of vehicles. So let's start with the automotive physics analogy, and I'm going to riff back and forth a lot between cars and planes. Just 1/5 of a modern non-electric car's fuel energy reaches the wheels and moves the car. Of that tractive load, the energy you need to move the car, almost half, rising as the cube of speed, heats the air that the car pushes aside, and most of the rest heats the tires and road. And only about the last 6% of the fuel energy accelerates the car and then heats the brakes when you stop. But it gets worse. 19/20ths of the mass you're accelerating is the heavy steel car. So just 1/20th of that, 6%, or about 0.35% of the fuel energy ultimately moves the driver. Both acceleration and rolling resistance depend on mass. So mass causes most of the tractive load. Now, automakers cut losses mainly in the powertrain, where the big losses are, the red stuff. That's harder than reducing tractive load, and it's far less rewarding, because saving 1 unit of energy in the powertrain saves only 1 unit of fuel in the tank. In contrast, saving 1 unit of energy at the wheels avoids 3 or 4 additional units lost in getting that energy to the wheels. So you're leveraging 4 or 5 units of fuel saved at the tank. Thus, we can double or triple efficiency in a fueled car without changing how it's propelled, or we can roughly quadruple to octuple efficiency by combining low tractive load with electrification. And the Electric Power Research Institute found that making EVs more efficient before they're electrified can cut U.S. costs of electricity, grid, and recharging infrastructure by more than $200 billion a year. So we should first reduce tractive load, then improve the powertrain, and then the powertrain shrinks for the same acceleration, F equals ma, less m, less a. So that saves more mass, and it also saves capital cost to help pay for the lightweighting. How can that lovely synergy work in practice? Well, let's look at the carbon fiber car that I drive. It is 55 kilograms lighter than a 2-seat 2009 Tesla Roadster. It was profitable from the first unit that BMW sold in 2013 and for all 250,000 units sold over the next 9 years, including mine. It's made from carbon fiber, which automakers had rejected as far too costly. But its carbon fiber was paid for by needing fewer batteries, the most expensive part of an EV, to move less mass. Also, fewer batteries recharge faster and need less electricity and less infrastructure. So the roughly 300 kilograms of saved weight then snowballed spectacularly, saving about 1.5 to 2.5 kilograms of secondary weight for each kilogram of saved primary weight. Part of that, of course, is the saved batteries. The assembly of this car saves 2/3 of the normal capital in water and half the energy, space, and time. It also eliminates the 2 hardest steps in automaking. It's much better for workers. It quadruples efficiency without compromise and with many driver advantages, of which my favorites are greatly improved visibility and half normal turn radius. Really handy in the city. Now, this design logic could also save up to 2/3 of the scarce battery minerals, and then there are 5 other multiplicative forms of efficiency that can manage the rest. BMW finished producing this model in 2022. There are calls to resume production, and if they decide not to do that, I suggested they give the tooling to Ukraine, which will know what to do with it. Meanwhile, Bloomberg New Energy Finance says that China's strategy for its 2030 flagship cars includes carbon fiber structures displacing 4/5 of the iron and steel. If that happens, it could flip the whole global car industry. China already makes impressive EVs priced as low as $5,000 or $10,000. So if China designed out another half to 2/3 of the costliest ingredient, the batteries, in its EVs, automakers elsewhere would have to follow suit or give up a lot of market share. Now, lightweighting is especially important because of mass decompounding, the snowballing of saved weight achieved by going repeatedly around the design spiral or design cycle. So first you make the vehicle light and slippery, so it takes only half as much energy to move it, and you enable smaller and more advanced powertrain and smaller, lighter chassis components, things like brakes and suspension. Those leave more packaging volume and more crush space. Then you go around the spiral again, making components smaller as structural loads shrink, because the less weight you have, the less weight you need. Lightness multiplies. But those recursions can also eliminate components. A good series hybrid car does not need transmission, clutch, flywheel, axles, differentials, drive shaft, U-joints, starter, alternator. Each of those 9 eliminated parts triggers another cycle of mass decompounding. So at first, the special materials and powertrain and design might seem too costly, the red part on the left, but after many recursive cycles of mass decompounding and simplification, you need so little carbon fiber and such a small powertrain that with the simpler manufacturing, the total cost can revert to normal or even less. Of course, I'm talking here about cost per car, the way we buy cars, not cost per part, not cost per kilogram, which is how many automakers still mistakenly think about cost. I don't know anybody who buys cars by the kilogram. Now, aerospace designers are a lot more sophisticated about saving weight, but often not yet enough, and not only about weight. I once asked a room full of the best designers at a top airframe maker, what's it worth, whole system, end-to-end life cycle cost of ownership, to take a watt of electric load out of your airplanes? Half of them didn't know the number, but they were sure someone else in the company did. The other half scratched their heads a bit and said, actually, nobody in the company knows that number because we never asked that question before. It's an important question, it's complicated, and we better figure it out. Well, based on the planes I fly in, I think they still need to figure it out. Now, strong lightweighting takes radical simplification. So let me tell you a story. Tesla's original Roadster had a 2-speed gearbox, and it kept blowing up because it couldn't deliver both 0 to 60 miles an hour in 4.6 seconds and the top speed of 125 miles an hour. So after 2 good gearbox manufacturers failed on this task, the chief engineer, J.B. Straubel, was griping one day. I said, I think the right answer is probably no gearbox, just a single-speed reduction gear. So he thought it over, and one day he came in and told his team, let's insource this problem to our core capability. We're electrical engineers. If we can make our motor produce 1/3 more torque, then we won't need the gearbox, and then we'll tweak the power electronics and software to match. And they protested, well, the motor's going to overheat, and you'll have to Band-Aid on some Baroque cooling system. He replied, don't worry, we'll figure out what's getting hot and give it better conductivity or a bigger cross-section. And so was born the 2010 Roadster 1.5. Eliminating that gearbox gained 16 kilometers of range, over 6 kilograms lighter weight, 30 kilowatts more tractive power, less noise, less maintenance, less warranty cost, and 3-digit fewer manufacturing dollars in an industry that will proverbially kill for a nickel. This little story and its competitive implications later triggered a major U.S. automaker's electrification revolution. Now, the same relentless pressure for simplification is now overcoming automakers' tendency to equip components with individual heating and cooling systems or forests of hoses. So the Tesla Model 3 instead used a single molded plastic heart whose 4-way valve redirects the thermal energy real time from where it is to where it's needed, optimally sequencing and cascading temperatures and figuring out who's going to need what temperature when. Likewise, of 5 separate power-related modules in the Chevrolet Bolt, stacked together in the left photo, Tesla's Model 3 eliminates 2 and consolidates 2 more into other modules, radically simplifying the system and achieving the same familiar suite of benefits. Airplanes offer similar opportunities, often more so. How low can the tractive load of automobiles go? Well, here's a table from a 2020 Society of Automotive Engineers paper I did called Reframing Automotive Fuel Efficiency. And it shows how my early 1990s analyses of 6 critical platform parameters inferred from historic data on concept cars and components what efficiencies production cars should be able to achieve by right around now. And those empirically grounded estimates were heavily criticized at the time, but a third of a century later, they are eerily close to market offerings, and their bottom line efficiency far exceeds what I estimated in the 90s. This kind of over-the-horizon radar signal is vital if you want to substitute accurate technological foresight for marketplace shocks. So I think collecting weak but real signals like this can enable some pretty accurate inferences about future aviation, since whatever exists is possible. So let me offer you some further examples to build on that idea. Remember how saving automotive energy by taking out mass or drag leverages much bigger fuel savings at the tank? Well, that's also true in planes, and it's even more valuable. With a 40-odd% efficient jet engine, each unit of mass or lift-to-drag ratio that you save in the airplane saves more than 2 units of fuel directly, and then even more with mass decompounding, which in 2020 was estimated as commonly a factor around 4 or 5. This multiplier also raises the value of saving onboard electricity. Even a quite efficient 787, drawing about 400 kilowatts of electric power at cruise, is not yet fully optimized. Optimization for full whole system life cycle cost, or value, might show, let's just make up an example, that maybe replacing a $20 coffee pot with a $200 vacuum super-insulated internal element coffee pot might save thousands of dollars worth of fuel each year. Boeing estimated that optimizing electric loads might add a couple of percentage points to the 787's roughly 20% gain in fuel efficiency, and even more when smart wiring and power management save a lot of heavy, complex wire. But I wouldn't dream of providing, say, thermal comfort in a building the way we do in airplanes. And we still have a long way to go with some fundamentals like taking out weight, even operational weight that's not built into structures. Taking a kilogram of weight out of a typical airplane is worth about $2,000 in present valued fuel cost. And that's at the fuel price before the Iran war. And it's worth even more on long flights where each liter you want to land with requires another half to 1 liter to carry the first liter across the Pacific. Once I was hitchhiking on a KC-135R military tanker, and I noticed a lot of heavy objects that didn't need to be there. Next morning, I briefed my observations to a couple of Air Force 2-stars. That afternoon, they launched a treasure hunt. It promptly found $2 billion worth of weight savings and hence fuel savings in that aircraft class, and then over $10 billion in all heavy aircraft classes. That's weight that nobody had been responsible or rewarded for noticing and taking out. Likewise, as an airplane passenger, I notice uneven attention to weight. They sweat the details of lightweight toilet paper and lightweight magazines, or take those away, but they overlook really heavy tray tables and, until very recently, heavy galley carts. And airframe makers could do a lot more with basic structural weight, too. Our lightest passenger planes are still only about half carbon fiber composites by mass. But 3 decades ago, Dave Taggart at the Lockheed Martin Skunk Works led for DARPA the design of a 95% carbon composite advanced tactical fighter airframe that was 1/3 lighter but 2/3 cheaper than the 72% metal base design for this joint airstrike technology, later called the Joint Strike Fighter. Here's a closer and flatter look at it, and here are some of the benchmark numbers. So this is a 735 kilogram lighter airframe with 3 or 4-fold lower production costs. So that showed, as BMW later did for cars, as you saw, that ultralighting doesn't need to cost more and it may cost less. And the cost would be even lower today because the leader of the Skunk Works project then moved to RMI in 2000 and led our hypercar spin-off's development of a cost-effective SUV with half the normal weight and 4 to 6 times the normal efficiency. And a team led by another RMI engineer at that spin-off, Dave Kramer, now longtime head of advanced composites at Apple, where BMW's iProject leader then led the Titan car project. So that team at RMI later developed our carbon fiber midsize SUV, which we called Revolution, and its airframe-inspired body, suspended from rings, not built up from a tub, had just 14 parts, each made with one low-pressure die set, saving 95 to 99% of the tooling cost. Each part can be lifted in one or two hands with no hoist. The biggest part, the side of the car, I can briefly lift with one finger, and the parts then snap precisely together for bonding, self-fixturing, detolerance in 2 dimensions, so you don't need the robotic body shop. By laying color in the mold, you can nearly eliminate the paint shop. So there go the 2 hardest, costliest steps in automaking, saving about 80% of the manufacturing capital. That plus the 2/3 smaller powertrain pays for the carbon fiber, making the ultralighting approximately free. And as you saw, BMW later validated these 1990s claims with its i3. Now, this car design was stage 2 of an effort at RMI to revolutionize the global auto industry. Stage 1 had developed my hypercar concept around 1990-91, initially validating it with GM and other automakers. But after a couple of years, it became clear that GM was culturally unready to collaborate, especially with a small nonprofit. So RMI's board told us to take the concept out to the whole industry. So we did something a little sneaky in 1993. We open sourced it. We made it free like Linux software. Hard to beat free. And then I got most of the world's automakers worried that their competitors would do it first. By 2000, that tactic had leveraged our $2 or $3 million of philanthropically funded R&D investment into more than $10 billion of industry commitments. It sped up the Japanese hybrid releases, Honda's Insight and Toyota's Prius, by, they told me, close to a decade, and it got serious lightweighting efforts underway. And then our hypercar sped off in 2 Tier 1s designed Revolution. Unfortunately, we sought production capital in November 2000 just as capital markets collapsed. Bad timing. But our design intrigued and inspired automakers. So as you saw in 2013, 20 years from our open sourcing, our fiber forge manufacturing process entered the supply chain, and BMW, our #1 target of influence, sold the first hypercars, which I've been driving since 2016. Now, this Revolution SUV we designed had what came to be called Gen X, Gen Y, active outdoor lifestyle luxury crossover styling. It could carry 5 big adults in comfort, plus up to 2 cubic meters of cargo. It could haul a half ton up a 44% grade. If you fold down the right-hand seats, you could carry 2 adults and 2 standard kayaks inside. And being half normal weight, it could accelerate 0 to 60 miles an hour in 7.1 seconds with a 1-liter hybrid engine. Maneuver and crash safety improved further with no steering wheel and no pedals. You steer, accelerate, and brake with a joystick inserted in the socket on either side of either seat. The radically integrated and simplified design put nearly all functionality in software, which we've now seen in a lot of cars. And think of this as a computer with wheels, not a car with chips. So it's a 24-year-old dream of a Tesla or a Sony PlayStation 10. Way cool. And a lot of cars on the road today look remarkably like this 26-year-old design. Our team's fiber forge process for mass producing competitive structural carbon fiber parts made what I call my carbon cap. This is just a little test piece which we can pass around. It was made in 1 minute 17 years ago for military ballistic helmets. And then we made a lot of airplane parts like composite window frames that went from concept to commercial flight in 6 months. We sold the manufacturing technology to a German Tier 1 pressmaker in 2013. And this process, as embodied in this machine released 3 years later, can make a complex 2x2 meter structural carbon fiber part in 1 minute, or more than 1 million smaller aerospace parts each year. You could make it several fold faster if desired. And probably not used to plastic sounding like that. I mentioned this technology just in case you think that making advanced composite airplanes and their structural components has to be small and costly. Now, advanced composites are slowly and incrementally displacing metal. Current trends include carbon fiber wings, elliptical fuselage forms that have like a 787 passenger compartment on top of a skinnier 737 size cargo hold, so you can fit in more seats with less drag and less weight. But a lot of components are still made of metal that shouldn't be, and the barriers are not mainly technical or economic, but cultural. You see, radical designs like that 95% carbon composite Joint Strike Fighter airframe require revolutionary design mentality, designing in the future, not in the past. When the Soviets shot down Francis Gary Powers' U-2 spy plane in 1960, Kelly Johnson, who ran the Skunk Works, did not say, "I'm going to design a slightly better U-2. He said, in paraphrase, "I want to own the skies for decades, so we'll design a Blackbird SR-71. I don't know how, but we'll figure out." And they did. It took about 13 months. Because, you see, Johnson understood that such an airplane was impossible within the conventional design context, because design is like a rubber band. If you try to stretch it too far from the conventional design space, you encounter more and more resistance, and eventually it breaks. But if instead you jump to the new design space you aspire to, then you can stretch the rubber band back to fit technologies not yet ripe, and then as they mature, the rubber band relaxes to where you want to be. Ultralighting requires not just smart and uninhibited designers, but also organizing them differently. Dave Taggart brought us from the Skunk Works our Revolution SUV's design process. We had 7 engineers all sitting around the same table, collectively responsible for dauntingly ambitious whole vehicle requirements that the industry had no idea how to meet. But each engineer also owned one major vehicle system or function. Here's the trick. For those, we deliberately wrote no requirements because we didn't want him to make his problem into her problem. We wanted to make the whole team design a highly integrated vehicle together. So 2 engineers were not comfortable without their very own requirements. We replaced them in the first week or 2, and then it went great and we got the intended result. Toyota asked us how we did it. We told them. In 2007, out came the 70% lighter 400 kilogram carbon fiber hybrid concept car they called a 1X, 1 over X. So you see the ultralight carbon fiber electrified hypercars that I invented 35 years ago, we designed with industry 26 years ago, developed design methods that Toyota used 19 years ago to design that 1X, the 70% lighter carbon fiber hybrid car. Similar methods entered the market in 2013 with that popular and profitable BMW i3 you saw. But even 1-ton lightened aluminum fleet vans like this hybrid that another RMI spinoff developed and road tested in 2009 could save a fifth of U.S. auto fuel at lower life cycle cost with no subsidy. And carbon fiber autos made in our simplified way at normal cost could save more oil than Saudi Arabia lifts. At an extra cost that a decade ago was under $18 per saved barrel, today it's close to $0 or less. 2/3 of the EVs made in China last year are already at or below sticker price parity with steel internal combustion engine cars. So they save oil at negative capital costs, and so do 2 popular U.S. electric vehicles. Now, aeronautical structures could be made in radically different ways that Kelly Johnson would have loved, leapfrogging past the bulk advanced composites you've been looking at. 7 years ago, MIT Center for Bits and Atoms introduced a flexible lattice structure, illustrated on the left by this 4.3 meter test structure, which is 59 times, not 59%, less dense than a typical metal aircraft wing. This kind of structure has the strength of elastomers, but the gossamer density of aerogel. It can also eliminate movable flight surfaces because every part of its entire shape passively adapts to optimize continuously for real-time flight conditions like a bird's wing. So thousands of such identical anisotropic molded polymer little cells, ordinary engineering plastics like ABS, can be assembled by swarms of program robots or grad students, whichever are cheaper, into an airplane of any desired shape. So this cutting-edge technique, lattice and membrane, opens revolutionary prospects for lightweighting, aerodynamics, and cost reduction. It's been prototyped as an airplane for Airbus and as a car for Toyota. You could even make it into a vacuum balloon, buoyant but crush-proof in air, and a big vacuum balloon could lift 24 times the payload of a jumbo jet. Alternatively, these hooked-together miniature structures are as strong and stiff as solid structures, but they're up to 90% air. They don't even use carbon fiber. And after carbon fiber could come Miralon's or Dexmat's carbon nanotube structures with up to 10 times higher mechanical performance. And now we can make similar near nanotubes from sugar and water and sunlight via the bacterial enzymes that hummingbirds use to weave their nests. Another approach uses nanoprinted metals with optimized microstructures. Airbus's collaboration with Autodesk generated this 45% lighter partition for the A320 and exciting design concepts for whole airplanes. And of course, the same logic applies to 3D printed metal parts as it does to bird bones. As usual, nature has done all this before. And there are firms like Nanocomp Technologies that already make strong ultralight carbon nanotube electric conductors to displace the heavy copper wires in satellites and in aircraft. Extinct pterosaurs, the biggest flying creatures in the history of life on Earth, had wingspans up to 10 or 12 meters, 3 times the biggest thing that flies today, living thing. And that's thanks to bones with paper-thin walls stiffened by internal struts. Complex porosities made the bones much lighter, slightly bendier, and able to combat and heal cracks. So there's now a field called paleobiomimicry, applying designs from 1/6 of a billion years ago to improve today's aerospace structures. Now, of course, airplanes have long been getting more efficient. Models that the U.S. certified from 1960 to 2000 cut fuel intensity by 70%, half from better engines, half from better airframes. And that progress remains on such a steady and plodding course that Boeing's NMA, or 797, was expected to hit in 2025 exactly the efficiency bullseye we had estimated in 2004. But uncertain and often cash-flowed customers and incremental thinking and restricted vision and market turbulence and then Boeing's deculturation make the industry's trajectory too slow. We're raising efficiency just by 20% per generation. At that rate, it could take another century to do what we knew how to do a decade ago. By then, we're cooked. And aviation is doing 6 or 8% of the cooking. Now, next generation options are well known, effective, profitable. Advanced composites will lighten aircraft by at least another 20% and enable the elliptical fuselage. Morphing wing technology can save over 10% of fuel in new clean sheet designs. Over 3% retrofits, cut noise 10 decibels. Geared turbofans can be 15% more efficient than conventional jet engines. Blended wing body designs can often save over 40% if we change manufacturing and the boarding and deplaning operations. And a lot of other available innovations get powerful in combination. And back in 2013, NASA did a roadmap for seeing 50% fuel savings from the 2015 baseline as being available by 2020, 60% savings by last year, as shown in the right-hand yellow column. But airframe makers moved much slower to adopt these pretty obvious technologies. And just to make this real, designs like these illustrate how more ambitious combinations of current technologies can boost the U.S. fleet's efficiency cost-effectively by 3 to 5-fold over the 2005 level. So the upper 3 designs are from Boeing, NASA, and MIT. They're more than a decade old. The lower three are a few years old. Both sets can save 50 to 80% of the fuel versus 2005 best-in-class or versus today's fleet. They use strut-braced or truss-braced wings, riblets, and other surface treatments like shark skin. Advanced composite structures, hybrid electric propulsion with gas turbine-assisted takeoff and range reserve but electric cruise, potted or buried propulsors, boundary layer ingestion, some blended wing body designs like the kind of the one in the lower middle, other expanding innovations. Well, the then chief scientist of NASA Langley, Dennis Bushnell, told me 7 years ago that just proper application of truss-braced wings with advanced aerodynamics can raise the lift-to-drag ratio from about 18 or 19 with tube and wing designs we fly today, or 22, 23 with blended wing body, to 40 or 60 or more. So 2 or 3 times better than today's fleet, while continuously reducing weight. There's a Swiss laminar flow wizard named Werner Fenninger, who even designed lift to drag as high as 100, nearly 5 times current norms. Bushnell suggests further adding other refinements like thrust vectoring from fully aft propulsors to eliminate the tail, and replacing landing gear and heavy brakes, which total on the order of half the fuselage weight, with lower impact automatic landing and deployable parachutes for refused takeoffs. So there's still a lot of hidden treasure. And even simple changes can be effective. Sometimes if I'm on an old plane, I look out the window as it lands, and I've seen the flaps extended by a hydraulic and mechanical system that the wizard of electric actuators, originally a farm boy gearhead, rightly calls farm machinery. It's heavy, unreliable, costly to buy, costly to maintain. It does not belong in an airplane. He would replace it with a 5-fold more durable, far more reliable and reparable, and much cheaper hinge line electric actuator that cuts the overall system weight by 3-fold. Next, we can eliminate hinged flight surfaces. Like the Wright brothers' bendable canvas and wood, flight surfaces can now morph in real time to adapt to flight conditions, leaving the surface and the airflow smooth, as in these two methods. The first method has entered the supercar market in front and rear wings that morph to maintain downforce at any speed. There's an Aston Martin that does that. It's also expected to save about 2 to 11% of the fuel in planes. The Air Force has committed to deploy it on several hundred planes as soon as they get through the flight tests. And the second method uses the lattice and membrane structure that you just saw. And actually, nature is very rich in great aeronautic designs like this tropical cucumber seed that can glide for hundreds of meters. Not to mention the California condor. Besides all its advanced geometry, structures, and controls, I especially like the fully integrated system design and advanced manufacturing techniques. Now, can biomimicry raise propulsion efficiency? An Australian naturalist and sea captain buddy of mine, Jay Harmon, imitates the Fibonacci structure in natural vortices, like that running out the bathtub picture on the left, to make super efficient pump and fan rotors on the right. That tulip-shaped rotor can spin underwater at thousands of RPM with no cavitation. Now, your body has on the order of 100,000 kilometers of fractal blood vessels. And if they had the design and friction of standard industrial piping, you would need a heart bigger than your body. Very inconvenient. But your third of a kilogram, 1.5 watt heart suffices because your bloodstream uses laminar vortex flow. Airplanes don't use it yet. They should. Disclosure, I own about 1,000th of the company here. Now, such rotors can empirically raise pump and fan efficiency by 20 or 30%, not quite violating the pump equation, and computed and observed pump behavior now match up nicely. Some of PAX's diverse super-efficient fans, propulsors, winglets, and hulls are now on or entering the market, and remarkably, this is a real head-scratcher, their efficiency gains are independent of scale and independent of Reynolds number. So For air as for water, cheaply converting standard fuselage airflow to laminar vortex flow or toroidal flow regimes by adding a Fibonacci spiral of little veins running back from the nose can cut drag, and in one early torpedo trial can cut it by 14%. PAX's household fans are a lot more efficient and quieter than conventional ones. The latest one at the bottom uses 50 to 85% less power per unit of flow than its competitors from good firms like Holmes, Vornado, and Dyson, and provides higher air velocity with far less noise. Gee, I wonder if its principles might yield more efficient propulsors. Safran and GE's joint venture CFM International is testing an unducted or open rotor with one rotating stage and one stage of non-rotating variable pitch blades. Bypass ratio over 70 versus 10 for the giant 777 engine with its carbon fiber blades, and a 20% fuel savings expected in service by the late 2030s, mid-2030s. I wonder if such designs might benefit from subtle Fibonacci shapes like Harman's biomimetic fan blades. Or there's another suggestive innovation, rediscovering a 120-year history with over 160 patents. That's the award-winning toroidal propulsor for quiet drones developed at MIT Lincoln Lab, mainly by an intern. They were working on ring wings. That's an old concept said in the patent to improve lift to drag by 40 to 60% compared with the linear wing. You see, about 35 or 40% of the drag of a typical aircraft is due to vortex formation at the wingtips. But the toroidal propulsor has no wingtips. It wraps back into itself, and it may weigh more or maybe less per unit thrust, depending on materials. Now it's being mass-produced for quiet drones. Guess who wants those? And variants on the 1924 Prattle box wing, like the C-wing, also merit attention. There's also parallel development by a musician who wanted to abate annoying drone noise, and it's now been successfully commercialized as a marine propeller with closed-loop blades. You can get it 3D printed from online makers or in this elegant marine bronze from Sharrow Marine. They're now in a manufacturing collaboration with Ford. Air and marine versions can reduce fuel use and acoustic signatures. Okay, now let's combine lightweight with advanced aerodynamics. 5 years ago, I visited an ex-Los Alamos physicist, Bill Otto Sr., and his team. He'd been chief scientist avionics for the B-1 bomber. And since 2007, his firm was developing this radically optimized plane, demonstrating 59% lower drag than a standard business jet, thanks to highly laminar flow over practically the whole fuselage, wings, and tail. And all the critical areas have no rivets, no seams, no gaskets, no gaps. So this initial design with just a 52-foot wingspan aimed at type certification by last year as a $5 million business plane with a stand-up cabin height of 6'2", longer range than a 737. They did 3 years of flight tests, and then they decided to leapfrog to bigger models. And that superlaminar flow they demonstrated is clearly feasible in regional jet size, and as Airbus work suggested, probably up to about 737 size. But all sizes could blow up aviation business models like hub and spokes, because smaller, cheaper planes are perfect for rapidly emerging point-to-point route architectures, serving any of over 5,000 U.S. airports. Now, this plane on the left had an initial engine that was a 500 horsepower aluminum turbo diesel, Russian designed, German made, burning any fuel, including 100% SAF, but that's not the only option. 4 years ago, Otto Aviation confirmed plans for a mid-sized 2027 version powered by a ZeroAvia hydrogen fuel cell system. That powertrain's already flown in a 19-seat test bed. It's been tested as one of 4 engines in a Dash 8 turboprop, and its operating economics should beat even the ultra-cheap diesel due to even lower drag, less propulsion system maintenance, cheaper fuel. And now electric designs look promising because super efficiency displaces heavy batteries. So now Otto Aviation, renamed Otto Aerospace, has shown a transonic, superlinear, super mid-size, very popular business jet size, 62-foot wingspan, 4 to 9 passenger, 6'5" stand-up, virtual windows, Mach 0.82, called the Phantom 3500, with a transcontinental range at 51,000 feet above contrail formation. It cruises at about 115 gallons per hour. That's 60% less than normal. It cleared preliminary design review 2 weeks ago. It should fly late next year, and they project a half normal price, cheaper to buy and run than Elon Musk's over 70 million Gulfstream 650s. It's planned to enter service in 2030. 30% less drag than usual, over 50% less mass, so it fits under the 19,000-pound limit for simpler, faster FAA certification called Part 23, even though it has over twice the cabin volume of a normal Part 25 jet in its class. In case you wonder if it's credible, the fractional operator FlexJet just ordered 300 of these, worth over $5 billion. Benefits compound. Greater lift-to-drag ratio reduces fuel volume and fuel weight for a given range. Less fuel means smaller wings, smaller powertrain, smaller structures. So a 30% drag reduction compounds into a 60% fuel saving. Moreover, sustainable aviation fuel's higher price is more than offset by fuel savings. So you could get carbon reductions upwards of 90% and probably 50 to 90% reductions in ultrafine particle emissions better than free. The expected carbon emissions, even on Jet A, are virtually identical to those of common electric road vehicles. And the panoramic digital windows, which they call supernatural windows, save weight, improve laminar flow, promote thermal and visual comfort, and make the cabin 20% bigger. Integrative design in action. By the way, in 2011 and 12, EADS, now Airbus, published a provocative technical design study for, guess what, a largely laminar flow bulbous pusher fan, regional turboprop, 900 nautical mile range, some basic efficiency improvements, about 25%, smaller batteries, and then with mass decompounding, you could reverse more than half of the near doubling of weight from electrification, so the battery needs were milder. And the authors concluded that typical payload and range missions flown today can thus be realized with 750 instead of 1,000 watt-hour per kilogram batteries. Well, I was correct in 2011. Now we have more ways to do much better. So this is exactly what happened with battery electric cars. Even I thought in the 90s that battery cars were, as a Dutch expert said, cars for carrying mainly batteries, but not very far, not very fast, or else they'd have to carry even more batteries. No, I was wrong about that. The cars, powertrains, batteries all got a lot better, and together changed the game. Notice the together part. Now I own 2 great battery electric cars. I wouldn't dream of going back. They're better than fossil in every way. And this need not depend on exotic materials. As RMI spinoff Bright Automotive's aluminum van showed 17 years ago, you can do a lot even without carbon fiber. Here's Lucid's Air model, the Motor Trend car of the year 4 years ago. It used a compact powertrain to help fit a spacious luxury interior into a mid-sized package. And because it's so efficient, EPA rated it a record 512-mile range with 0 to 60 mile an hour acceleration in 1.9 seconds. Can your gasoline car do that? Will your neck tolerate it? Here's a developmental car Mercedes did 4 years ago, getting the equivalent of 252 miles per gallon. 95% battery to wheels efficiency, excellent 0.17 drag coefficient, light and curb mass, and the range was tested at over 1,200 kilometers, 747 miles, with a battery sized for a compact EV. The battery pack's 30% lighter, 50% smaller than in the comparable production model. This shows you how fast batteries are evolving with the help of electric race car technology. So range anxiety will become as obsolete as the speed of your modem. And notice this sedan's mostly metal, so there's more efficiency and range on the table. Some of its powertrain is in this year's CLA electric luxury sedan. Sells for about $50,000, maybe the cheapest Mercedes on the US market. just an 85 kilowatt hour battery. Okay, now the next efficiency leapfrog is emerging from a couple of solar-powered hypercars, both from little firms I've advised. They are now ready to mass produce. The first one should enter that late this year. Most drivers will never need to recharge this two-seat electric vehicle because the solar cells on top capture enough energy to drive about 40 to 60 kilometers a day. It's as if your present car magically added 2 gallons of fuel to its tank every day you park it outside. To make a long trip, you can quickly recharge the tiny batteries, look at the lower left photo, with household electricity, and you can buy batteries for ranges up to 1,000 miles. Now, my BMW and Tesla electric cars are among the most efficient you can buy now, but this two-seat vehicle with a very crashworthy composite body will nearly triple Tesla efficiency to 343 miles per gallon equivalent. Then there's the Dutch firm Lightyear, got ready but not funded to produce this 5-seat, 4-wheel, light, very aerodynamic car whose 5 square meters of solar cells gives it 251 miles per gallon equivalent, so it can add 12 kilometers of range for every hour in the sun. So the charging infrastructure that others have to pay for, these super efficient vehicles aim to bypass. And even they can be further improved. The 4-seat Edison 2 engine-powered winner of the 2010 Automotive X Prize used in-wheel suspension. And for 4 seats, it weighed as little as 322 kilometers. That's about 3 times lighter than the Aptera on the left here. What about aviation propulsion? Well, in gas turbines, the National Academies expect several more decades of 7% per decade efficiency gains beyond the current roughly 55%. And there's a lot of examples of that I won't go into, many of them involving 3D printing and some with geared turbofans. And the best of these innovations is promising in the 2030s to use at least 25% less fuel than earlier engines. And yet, coming up fast in the outside lane are electric and hydrogen-powered airplanes. Hydrogen-powered usually with fuel cells, as I'll sketch shortly. And many of these have long been in military use, and then they enter the civilian sector. So the maker of the most advanced always aloft military solar airplanes and the Switchblade backpack portable drones for Ukraine is the same company that also makes my charger for my BMW EV. Now, Ukraine is evolving drones in days, and they're making many millions per year, defining the outcome of Putin's war. But those new techniques are speeding civilian innovation. Conversely, military drones grew out of Chinese hobbyist drones and used their high-volume parts. A commercial glider spawned an Air Force surveillance drone now operating in the Middle East, costing nearly an order of magnitude less than a Reaper drone, but carrying a 400-pound payload for 80 hours. So the civilian markets are big enough to drive rapid innovation. In select U.S. cities, Walmart and Amazon are now using 70-mile-an-hour drones to deliver packages to your door, actually your front or backyard or driveway, in under a half hour. They just lower it down from 150 feet up and fly off. Now, among the critical technologies for electric cars and planes, there's one other category to mention, motors. They may be evolving fastest. Some powerful aviation motors are now 10 times lighter than we use in today's standard electric vehicles. Some might look like standard radial flux designs, but axial flux designs, although harder to make, can have half the volume and 4 times the torque. The best axial flux aviation motors now sold in the middle deliver 25 to 28 kilowatts per kilogram. That's nearly 3 times more power dense than the best EV motors. Twice as good as the best e-racing motor. And this example, stacked to a megawatt, beat the Air Force's 20-year goal by a factor of 5. Now look at the right. Last October, the firm that the founders sold to Mercedes while keeping its aviation division announced they just demonstrated an astounding 59 peak and around 50 continuous kilowatts per kilogram. Just try to visualize that. That's 3 to 7 times better than the radial flux rivals. And if you use that as a hub motor, that little thing gives you over 1,000 brake horsepower per wheel. What the hell do you do with that? It's going to smoke your tires rather than accelerate the vehicles. So sleeker and lighter planes need smaller motors and batteries than these, but that just saves more weight, more mass decompounding, and you're not suffering lower efficiency as you do when you make a gas turbine smaller. Top analysts now agrees EPs will generally have lower capital and operating costs than fuel planes, and that will drive their rapid adoption in both commercial and private aviation. By the way, lest you worry about critical materials, many fine light motors, both induction or asynchronous and reluctance machines, have no permanent magnets. And there are two kinds of supermagnets containing no rare earths. Of those, iron nitride promises up to twice the strength of the rare earth magnets, and that's entered the market. Inverters are progressing from silicon switches through silicon carbide, now common, to nearly lossless passively cooled gallium nitride, or GaN. Kilovolt silicon carbide switch ratings now make wiring small and light. So remember that Lightyear Dutch car? That has a 97% efficient powertrain, 2 points ahead of Mercedes. The best e-racing motors and inverters each get around 99% efficiency. Now, electric flight, in short, is becoming practical because many diverse technologies, not just better batteries, are converging in this vast Cambrian explosion of innovation. There are scores of serious and skilled and amply funded developers pursuing over 200 designs for bigger platforms and over 1,000 designs for urban air mobility vehicles. They've won over 12,000 orders for types with up to 30 seats from at least 55 intending operators. 8 automakers are involved. A year and a half ago, McKinsey estimated a future air mobility order book, not all of it firm, exceeding 21,000 odd aircraft worth $118 billion. That's more than the aircraft in the commercial aviation order book. Bloomberg last July counted 21,000 electric aircraft orders, most conditional. FAA last year estimated advanced air mobility departures could rise to about 7,700 daily flights in year 6. And already over 9,000 electrical vertical takeoff and landing, or eVTOL, air taxis, millions of drones, military R&D are enriching the electric aviation ecosystem. Joby, which some of my students work at, are planning an eVTOL taxi service this year from downtown New York City and LA to JFK, Newark, and LAX airports. That looks on track, and they price it at the lowest helicopter fare with as little as 1% of the noise. Prices by 2030 could match the premium car fares you pay now in Uber. Joby last quarter had $2.5 billion cash and a $10 billion market cap. It's in the last stage of FAA approval for its vehicle and for Delta, ANA, and Virgin Atlantic sponsored Uber integrated New York airport service. Archer, another leader, hopes to start serving United this year in New York and Chicago with eVTOLs. Stellantis produces its vehicles in Georgia. United has put deposits on 200 of them. Now, to be sure, it's not all good news. German eVTOL firm Lilium and Israeli-American developer Aviation, even after maiden flight, both collapsed. Several firms got absorbed, but some business failures were expected. New players are emerging. And the 8-year survival rate of the 2018 founding cohort of developers is around 58%, which is better than any other aviation segment. Private eVTOLs are emerging with half-hour endurance, like China's YivTOL for $60,000. It's a personal product. Dubai has built the first 4 of its vertiports. And the biggest uncertainty remains timely regulation. FAA fell behind, some developers stumbled, the pandemic slowed everybody, but some type certifications are well along, several are expected this year. And until then, the White House has an eVTOL integration pilot program to build a pathway for limited early operations spanning 26 states before type certification. So happily, flight without fuel can very soon start resolving communities' CO2 and air pollution and health concerns by eliminating emissions and turbine and rotor noise, just as in ground vehicles. Now, at whatever pace eVTOL air taxis become common, electrification will present new challenges and new opportunities to both airports and carriers. Competition between advanced biofuels and electricity and power to fuel and hydrogen is going to turn airports into integrated transport and energy hubs. It'll probably use distributed models, be designed for resilience. Electric air taxis are going to use more energy than electric ground taxis. Collisions are a lot more serious if they happen in the air. There are real security concerns like using drones to deliver bombs. And if you like congestion in 2 dimensions, you'll love congestion in 3 dimensions. So eVTOLs are going to need careful foresight. But first of all, will electric planes actually take off in the market? Or are the skeptics right that they'll never fly? Well, if you think EPs are pie in the sky, you might consider whether this who's who of vendors and operators of electric planes all got it wrong. Beta's 5-passenger eVTOL has flown a 600 payload, 386 nautical miles. Some skeptics may need to reconsider papers like one eminent aeronautical engineer's widely circulated screed 3 years ago called The Total Impracticality of Electric Aviation, which found that even a 50-mile range was infeasible and concluded that electric aircraft can never be more than expensive toys. Well, we'll see. I just ask you, how many of the firms in this chart would you like to bet against? How about all of them? And notice this is a 4-year-old chart. Or consider these counterparts in the hydrogen plane ecosystem. Now, to be sure, Airbus just slowed down its hydrogen plane program by 5 or 10 years, but mostly on infrastructure. And as we've seen, tenfold carbon savings offer juicy economics without hydrogen. Hydrogen does get easier as planes get far more efficient and hydrogen production gets decentralized. So I think it's pretty likely that incrementally minded incumbents and commentators are deceiving themselves and likely to miss their flights. The big question is how far hydrogen can carve out and defend markets against ever stronger electric competition that's already shrinking its use cases. Of course, top of mind for seekers of flight without fuel is battery energy density. At least 3 firms have doubled the smartphone pouch cell's energy density to 400 or 500 watt-hours per kilogram. That's about 3/4 of the pack density that the Academy said in 2016 would take 20 years. Looks like they're about a decade off. Several solid-state battery firms are now claiming cell level 700 or even 800 plus watt-hours per kilogram on the lab bench. And increasingly, that's integrated vertically with electric aircraft design. Think of the Chinese lithium battery giant CATL. 3 years ago, they announced a condensed battery with cell energy density 500 watt-hours per kilo. And they also mentioned their partnership had tested a 4-ton electric civil aircraft. And they expected in the next year or 2 from now to release an 8-ton version with 2,000 or 3,000 kilometer range. Well, that kind of company can move real fast. And indeed, initial uncrewed heavy lift eVTOLs with 400 to 800 kilo payloads, 200 kilometer an hour speed, and 200 kilometer range are today built, certified, and commercially hauling freight in China. But as the NASA authors I began with noted 12 years ago, 500 kilogram or watt hours per kilo at the cell level enables short-haul electric planes immediately, moving into medium haul starting in this decade. And also, as Chalmers in Sweden has shown, you can do a carbon fiber structural batteries. Large area batteries or ultracapacitors or both that eventually form the airplane's skin and structure while storing electricity, and the battery stiffer than aluminum, which must be pretty stiff because we use it right now for airplanes. ARPA-E has a Propel 1K program aiming for 100-passenger, 1,000-mile electric aviation, and they've funded a dozen teams developing 1,000 watt-hour per kilogram and per liter net energy storage systems. Already, lithium metal anode batteries are offering twice traditional lithium-ion energy density. Some production models are better. And as we saw, most importantly, battery energy density is fungible with platform efficiency, only more so because of mass decompounding. So already, especially with some of the high-density sulfur-selenium packs, it looks like you can get 280 kilometers with 90 passengers, but if you reduce the empty mass fraction of the plane, you nearly quadruple market coverage, or 15-fold increase for turboprops. So the key is really platform efficiency more than batteries. Now, I'm nearing the end here. I know it's long. Thank you for your patience. But I've been riffing back and forth between the aviation and automotive revolutions because they inform, supply, and feed on each other. Planes do go faster than cars, so is their innovation. And in both, the major drivers of innovation may lurk outside your system boundary. We have EV batteries today because mainly smartphone makers strongly incentivized battery life. That drove advanced lithium chemistries and efficient circuits. That made EVs possible, so Tesla built volume and made batteries cheap. Then our smartphones birthed our electric cars via consumer electronic companies like Panasonic and LG. What new drivers of electric aviation by non-adjacent industries will be obvious only in hindsight? And then, of course, there's the fuel cell path that turns electrochemically green hydrogen into electricity, pure water, heat, and nothing else. And so are electrolyzers, basically fuel cells run backwards. Even 5 years ago, the Chinese chemical giant Baofeng was switching a plant from coal to cheaper hydrogen, $2.7 a kilogram, made by its 1 gigawatt solar farm. And conventionally, paths to $1 a kilogram hydrogen look a lot harder than 2 years ago, but an unsubsidized $2 remains plausible with the downward trajectories of solar and wind. And then if you combine that with the powertrain advances from the British consortium with many powerful partners, ZeroAvia, you get some very fast progress, as shown here in their development path for this decade. And they may not exactly meet that, but someone else may. A couple of years ago, Joby demonstrated a liquid hydrogen fuel cell eVTOL, 454 nautical miles with 10% reserves. 5 months earlier, Bertrand Piccard announced a round-the-world 9-day nonstop flight planned for 2028 on liquid hydrogen. And the fuel cell planes are dramatically more reliable and lower maintenance costs than fueled engines. With hydrogen, as with electric flight, it is really unwise to stand with your back to a stampeding herd of technobison. Let me end with a few observations about intercontinental range. I won't dwell here on turbine or engine hybrid designs. They could have a transitional role, much as they did in cars. But automotive efficiency took us to once unthinkable solar-powered cars, Aptera. I think similar and inexorable trends are emerging in aviation. Now, the conventional fossil-free solution is obvious. Liquid hydrogen. There's been a lot of good work on that. Hydrogen is 2.8 times lighter than jet fuel, 4 times bulkier, so you need a whole new airplane design. but it could be more efficient than Jet A, enough to offset the liquefaction energy. And I've seen automotive cryogenic tanks with walls just millimeters thick. So a lot of exciting opportunities here to raise airplanes' established 3 to 5-fold potential efficiency gain to about 6 or 7-fold, or with the lighter motors and better aero, probably now over 8-fold. In case you were wondering, liquid hydrogen is safer than Jet A for a lot of reasons. If the hydrogen escapes, it does not explode and it doesn't pool like kerosene. Rather, it diffuses and burns upwards with a brief clear flame that cannot burn you at a distance. That's why nobody in the Hindenburg dirigible disaster was killed by the hydrogen fire. They were only killed by jumping out, or by the diesel fuel fire, or by the ignition of the canopy made of flammable cloth coated with powdered aluminum. It's what we would now call rocket fuel. Not a wise choice. So here's a side-by-side worst-case test of delivered hydrogen release on the left, draining a high-pressure gaseous hydrogen tank in a car at the highest possible rate in about 100 seconds, compared with on the right a small hole leaking gasoline holding 60% less energy. You can only see the hydrogen flame because there's salt in the sea air where this was tested. But the hydrogen flame radiates so little heat it barely warms the outside of the back window. The gasoline fire quickly turns into a barbecue. I would much rather have a hydrogen fire, but to start it you would need not a single tank hole, but the simultaneous failure of the fuel line plus 3 independent safety devices. Now recall how radical automotive fitness enables all kinds of advanced powertrain, as in our Revolution carbon fiber SUV, using an early fuel cell and using 1990s off-the-cell carbon fiber tanks that could easily carry hydrogen up to 10 or 12% of their filled mass. Well, Toyota's Mirai hydrogen car needs 700 atmosphere tanks, twice as much pressure as these. And it's awesome that they've doubled the power density and made the fuel cells cheaper 95% in 9 years. But they could have made those systems 2 or 3 times smaller by putting them into Toyota's 1X carbon fiber concept car you saw, instead of the Prius 5 platform that's almost 5 times heavier. And indeed, in our design, our SUV's efficiency made its fuel cell 3 times smaller. That means you can pay 3 times more per kilowatt. At a standard 80% experience curve, you would then need 32 times less cumulative production volume to get to competitive cost. So that would speed the hydrogen transition by a decade or two. And I think with or without hydrogen, the same logic applies to efficient planes. Here's just a little petting zoo of some of the ultra clean and super efficient planes coming at us. And they're still just targets promised to investors. Some specs, some dates will slip, but there are so many and so capable firms, I think they're unlikely all to fail. These are just a quarter of the industry plans I examined, which are a fraction of the total, and many are not yet announced. So remember that as Paul McCrady's AeroVironment team progressed from the human-powered Gossamer Condor in '77 to Gossamer Albatross human-powered flight across the English Channel in '79, to Solar Challenger, the first solar-powered distance flight. At the same time, McCrady was hatching the Sunracer solar car. It was so efficient, it won the first Trans-Australian solar car race in 4.5 days. That was 2 days ahead of the nearest competitor. So his breakthrough planes and cars inspired each other. Super efficiency can enable electric planes just like electric cars. And that's happening faster than you might think. I'm going to skip this eye chart, which just shows how in the airport near where I live, Aspen, Colorado, they're imprudently planning $1 billion rebuild of the airfield for bigger fossil fuels planes that would all get built right around when those planes are likely to start getting outcompeted by efficient electric planes that they're carefully not looking at. But if we buy enough efficiency, hydrogen electric and battery electric are no longer the only choices for planes any more than for cars. Could we imagine a flying analogy of the solar-powered, battery-buffered, super-efficient Aptera car? So that's my last 3 slides. Solar-powered flight already works daily in many military and a few civilian platforms. Photovoltaics took a pilot far into the stratosphere in 1999. In 2015, the solar-powered Solar Impulse 2 circled the globe on solar power, buffered by batteries half as good as today's. Airbus has commercialized a solar-powered platform designed to stay aloft for 200 or 300 days. Solar Flight's latest 2-seater can stay up as long as there's sun. And don't forget the simultaneous revolution in the photovoltaics themselves. With concentration, we're now at 47.6%. For little ones, we could probably get over 50. But without concentration, like on an airplane wing, a 3-junction cell has been measured at 36.9% around sea level. But at cruise altitude, there's 20 or 25% more sun, and there's nearly as much reflected from Earth and clouds below as captured from the sun above. So you put the coating on both sides. The temperatures are around minus 60 Celsius, making the cells more efficient. You also reduce absorption from oblique angles of incidence, but on balance, net efficiencies at cruise can be very high. And today's chip-making tools may also be able to lithograph flexible optical antennas and optical frequency nanodiodes with system efficiencies upwards of 80%. Some people think 90%. Until then, PV cells are costly, but generally less so over the years than fuel, plus the fuel to carry it. And the cells, carefully encapsulated so they don't break from flexing, are very lightweight. So are super efficient GaN power electronics. So platforms like Zephyr prove the power of combining such solutions. So, returning to our earlier question, can we make an electric plane like an Aptera electric car so efficient it doesn't need recharging? Well, I suspect we can if we combine the best proven methods of ultralight construction, super efficient powertrain and photovoltaics and buffer batteries, advanced and biomimetic propulsors, ambitious aerodynamics, combined with advanced treatments to keep surfaces clean and smooth, super efficient accessories and HVAC, virtual windows, far lighter landing gear and techniques, and other innovations. Do numerous recursive mass decompoundings until you're doing almost everything with almost nothing. Repeat until done. I'd like to do this massive synthesis in one giant leap, because all the parts exist. It may actually happen in pieces, maybe with a temporary hybrid stage, but I think probably leapfrogging over hybrids like car range extenders will yield better integrated design solutions sooner. They're a temporary fallback position if needed. They're not a good destination. And if we work very hard, I suspect that my grandsons may fly the Pacific in profitable solar-powered airplanes. Why not? So let's do the systems analysis with skills and tools I lack but the best experts have. Since solar power needs sun, we'll have to reschedule some flights so they don't escape or outrun the daylight they need. So solar flight is not a solution for all times and all places. Unless very light reversible fuel cells, lighter than batteries, do let us fly at night as McCrady's Pathfinder did. But even the mid-sized planes like that bulbous super Laminar thing you saw burning SAF in diesels, 8 times more efficient, thoroughly flight tested years ago using point-to-point route architectures, that could plug most or all of the gaps while emitting close to zero carbon. So winning on both capital and operating costs, they could quickly push out fossil fuel planes in virtually all missions. They will also have to compete with solar planes. Competition is good. And what it's telling us is aviation is far more decarbonizable than we thought, and that design and technology are moving a lot faster than strategy, policy, and regulation. So, to end, how do they start to catch up? Making this happen is a challenging opportunity that I offered the global aviation industry when keynoting the 2019 ATAG, Air Transport Action Group Montreal meeting, and then addressing ICAO, both sponsored by Boeing, both very warmly received by Airbus and major suppliers. And I offered there an implementation concept that many of them loved. Its quick takeoff, I think, could bring to fruition many of the technical ambitions I've described. You see, for a decade, we've had the technology to make 3 to 5x more efficient airplanes if someone would make them and someone would buy them. Now we see even greater gains clearly in sight. So why take a century to do this incrementally when we can leapfrog straight to it? Major airplane buyers, even if they have the capital, are understandably risk-averse. Airframe makers don't want to risk huge development investments for a radically better product that might not sell. So incrementalism continues as we squander fuel, money, talent, carbon budget, and precious time. Climate won't wait. Business as usual won't work. Aviation's license to operate will erode. Our shareholders, voters, and children will judge us negligent. But what if a powerful consortium of major customers, airlines, lessors, delivery and air logistics firms, the Pentagon, relieved the airframe makers' market risk so they could fully focus their skills and ambition? The buyers could collectively solicit a super efficient airplane by publishing very demanding specifications, very clean and at least quadrupled efficiency, and collectively commit to buy X copies a year for Y years at price C from whoever first brings it to market, with a consolation prize for the runner-up. This would elicit and reward innovation for the airplanes they're going to buy anyway, but unbundling buying airplanes from buying innovation changes the supplier's culture and brings out the best talents of their best innovators. That yields a very different product slate, reducing risk to both parties, but most of all to airplane buyers. This method is called a golden carrot, or advanced market offerings, or advanced market commitments. It's worked well since 1990 for over 20 diverse solicitations in countries from Sweden to France, from America to India. Never for something as complicated as an airplane, but I think we now know enough to seriously consider it for airplanes. That could decouple flying from climate change, and unlike carbon offsets, it could also slash fuel costs and the risk of fuel price volatility. So in this teachable moment about insecure oil supplies, it could greatly increase energy security and national security, and it could unleash a huge burst of innovation that could transform aviation forever. What are we waiting for? Thank you.